Okay, so we're gonna start with DHCP snooping. Just a heads up. So today we're gonna do a lot of layer 2 stuff. Then we're gonna go to the iOS NAT part and the zone-based policy firewall part of the iOS. So as I said the other day, yesterday, depending on how class goes, we may also run a smaller, like a couple of more hours on Friday. So at the end of the day, I'm gonna let you know if that's the case or not. So it may be that we're gonna run a couple more hours on Friday just to make sure we cover everything, because I don't want to rush over the topics. I just want to take time, explain them properly, and better off to run a couple more hours on Friday. In case you cannot attend that session on Friday, of course you're gonna be able to view it in a recorded format in the AAP section. So let's see why would we need this capability, this feature of DHCP snooping. We need that because of DHCP attacks. So as we know, the DHCP server is going to have a finite number of IP addresses which it can use to lease to its clients. And we have a couple of variations of attacks. One of them being that an attacker on a segment where a DHCP client is going to set a flood of DHCP requests with spoof source MAC addresses, which means that the DHCP server is going to lease all of its IP addresses to the attacker, because the attacker is going to send malicious spoofed DHCP requests with spoof source MAC addresses till it's going to deplete all leases from the DHCP server. So that means is that once the DHCP server has no more IP addresses to lease, it means that when a valid client shows up, the server has no other addresses to lease to that client. Like for example, looking in this diagram in here, let's suppose that, and that's going to be the use case of course for us as well. So let's suppose router 1 is going to be my DHCP server for VLAN 11, my DHCP server for VLAN 11, DHCP server for VLAN 11, and PCA and other clients of course are valid clients. This is going to be a legitimate or valid DHCP client. Before the client shows up in the network, what happens is that an attacker in here connects to that switch in the same VLAN, the attacker, and is going to send a lot of DHCP requests, each of them with a different source MAC address, with a different spoof source MAC address. Is going to send one request, so request number 1 with a MAC of A. Another DHCP request out there, request number 2, with a MAC of B. And so it's going to send thousands and whatever, a lot of number of those requests, till it's going to receive no more IP addresses from the DHCP server, which at that point means that the DHCP server is out of IP addresses to lease. So at this point, when our valid legitimate client shows up in the network, and also our client is going to send a legitimate DHCP discovery message, DHCP discovery, saying, hey, I want an address and other information. Is there any DHCP server out there available to give me that information? When he sends that discovery message, then even though router 1 is going to receive it, router 1 can no longer reply because it has no left IP addresses to lease to PCA. That's one kind of attack which can happen in the network, which at that point it means that because PCA doesn't have an IP address, it means it cannot have IP connectivity, which means that user cannot perform its job in the network. Another attack is going to be that a spoof DHCP server shows up on the segment. So now the attacker actually starts a DHCP server on the segment and offers rogue IP addresses to the DHCP clients, which can result either in a man-in-the-middle attack, or is going to end up that clients become isolated. So what this means is that given the same setup in here, VLAN 11, so we have VLAN 11 in here, and we have likewise again PCA is my legitimate DHCP client. So this is my DHCP client. And router 1 is my legitimate DHCP server. But what happens, again, the attacker connects in here in the network. and he starts a rogue DHCP server as well, a rogue, so unauthorized rogue DHCP server. And what's going to happen, the PC is going to send a broadcast UDP, because DHCP is going to run over UDP, and the discovery message is broadcast. It makes sense because I want that message to reach out all hosts in that VLAN. So the client shows up, router 1, PCA is the client. PCA shows up, is going to send a DHCP discovery message. So it's a broadcast message, the client saying any DHCP servers out there. And because it's broadcast, which one is going to send is going to replicate that message out to both the attacker and router 1. And what happens per DHCP design, both the attacker, of course, and router 1 are going to reply with a DHCP offer. So the attacker replies with a DHCP offer. Likewise, router 1 replies, and that reply reaches the client as well with a DHCP offer. But per DHCP design, if the client first receives the message from the attacker and second receives the message from the valid DHCP server, per DHCP design, the client is gonna continue its negotiation process with the first offer it has received, which is from the attacker. And this can easily happen if the attacker has, let's say, a faster CPU, which is going to process faster the discovery from the client, is going to respond faster. But of course, also in general, the DHCP server is not going to be connected in the same VLAN as the clients are. So in general, router 1 is going to be a DHCP relay. Router 1 is going to be a DHCP relay actually. It's going to relay that request. Is going to catch that client's discovery and relay it further to a centralized DHCP server. Because in a network with a lot of branches, you're not going to have, like thousands. Usually you have a centralized server. You don't have decentralized DHCP servers. Like in each location, you're going to have a DHCP server in there. Doesn't make sense to manage thousands of DHCP servers. You're going to have one or two centrally deployed for redundancy, which they take care of all IP addresses leases for your clients. So if this is the case, clearly the attacker's reply is going to come faster to the client as opposed to the message from the reply from the centralized DHCP server. Either way, what happens? So because the PC continues its negotiation with the attacker. So because the PC continues its negotiation with the attacker, so the client sent the discovery message, the attacker replied, so step number 1, step number 2, then the client sends the request message, step number 3, and the server sends the acknowledge message, step number 4. And at that point, the client is going to have an IP address list from the attacker. And of course, what the attacker is going to do with this rogue DHCP server, it is going to assign addresses from let's say from a non-routable subnet, like for example from, let's say, 20, let's put something private, from 192.168.1.0/ let's say 24. So PCA is going to get assigned an address of 192.168.1.1, let's say, with a default gateway of, let's say, 192.168, because in IPv4 we also assign default gateway via DHCP, that, let's say, 200. So at this point, if the default gateway doesn't exist in the network, then the client becomes isolated. The client cannot route traffic out of the VLAN because the default gateway is not reachable. But of course, if the attacker is smart enough, the attacker is going to self-configure itself on its interface in that subnet with that default gateway address 192.168.1.200. So I had a typo in here, so it's going to be the default gateway is going to be .1.200. So the attacker actually self-configured itself with the default gateway on that network segment that is going to assign to its clients. And what happens is that when PCA wants to send traffic out of that VLAN to remote destinations, you're going to send its traffic to its default gateway, which is the attacker. The attacker has a copy of the user's traffic, and if it's smart enough not to be caught, because clearly if the attacker just stops in here to receive the copy of the traffic, this user is going to call support saying that he doesn't have access in the network. But if the attacker is smart enough, he's going to reroute the packet out in the network to the real default gateway in the VLAN, which is router 1. So with this kind of attack, the attacker is like stealth. Nobody is even aware that he intercepts all IP packets from pretty much all the users in that VLAN. So depending what the attacker wants to do, he can either if he wants to get a copy of the traffic from the VLAN, he's going to use this attack. Otherwise, if he just wants to, let's say, perform a denial of service attack, he's just going to list to clients rogue addresses which are not routable with a rogue default gateway, which means the clients are going to become isolated. Regardless of the variation of the attack, this is not a good thing, clearly. So what are the solutions? And the first question is that, can port security prevent this? Because technically speaking, you might believe that, okay, let's speak about the first attack where the attacker was connected in here. The attacker was connected in here on that port, and he was sending a lot of spoofed DHCP requests with MAC address of A, with MAC address of B, and so on, in order to deplete DHCP requests with a lot of spoofed MAC addresses, in order to deplete the DHCP server's pool. So at that point, the DHCP server is going to left without IP addresses to list to legitimate clients. So if I enable port security on this port, which means that the attacker if I enable port security in here, which means that the attacker can no longer send Ethernet frames inbound on that port with different source MAC addresses. So it's not going to work because port security, as we know, limits the number and which MAC addresses can be seen inbound on a port. So the attacker can no longer generate DHCP requests with different source MAC addresses. But actually, per DHCP design, a DHCP server allocates an IP address to a client based on its DHCP client identifier, which is a value in the DHCP payload. So not based on the MAC address. The MAC address is used as a fallback in case the client doesn't attach to its request a client identifier. But all DHCP clients nowadays are going to have a DHCP client identifier. So to keep it simple, the DHCP server does not assign addresses to clients based on their MAC addresses, but based on their Ethernet MAC addresses, but based on their DHCP client identifiers. So what that means is that the attacker can keep the same MAC address across those multiple DHCP requests and just change the DHCP client identifier, which ends up in the same starvation attack is going to starve the IP address pool from the DHCP server. Because port security is going to see a single MAC address, port security does not do any kind of inspections of a payload. Port security only looks at a source MAC address from the Ethernet frame and is going to compare that source MAC address against its configured port security policy. So clearly, port security is not going to help in here. So the solution is to implement DHCP snooping. Now, this capability is only available for IPv4 DHCP. For V6, we have DHCP guard. It's a different feature. It's a layer 2 switch capability enabled per VLAN. And by the name, what it means that is the switch is going to snoop, which means it's going to intercept DHCP packets. So when I'm going to configure DHCP snooping, I want the switch to actually validate somehow, we're going to see exactly how, DHCP packets flowing in that VLAN to prevent those two attacks in there. So we need some kind of intelligence in there, somebody that can actually snoop, intercept, and validate DHCP packets on that VLAN. Now, once you're going to enable DHCP snooping for VLAN, then all ports in that VLAN are going to become untrusted from the DHCP point of view. So the outcome is that the switch for that VLAN will not allow DHCP server type messages on untrusted ports. Which means if you want DHCP to still work, you gotta go on the switch, and the ports facing your legitimate DHCP server has to be configured as DHCP trusted. So what that means, following the same example in here, is that you go on this layer 2 switch and enable DHCP snooping for VLAN 11, or for all VLANs where you have DHCP clients in there. In my case, it's only one VLAN. You enable DHCP snooping for that VLAN. Which what that means, let's also put the attacker in here. Which the attacker is also present in VLAN 11. So all of those three devices are members of VLAN 11. And now VLAN 11 has DHCP snooping enabled. Once that has happened, all of those three ports are untrusted from the DHCP snooping point of view, which means that the switch is going to drop all inbound DHCP server messages on those ports. So it means that if router 1 wants to send a DHCP server type message, like a DHCP offer, as a result of receiving a client request, or if the attacker sends a DHCP offer likewise, which is a server type message, the switch is going to drop them because they are coming inbound on untrusted ports, because all ports are untrusted by default, and it makes sense. So once we enable the capability, I am fully secure. I work in closed mode. Which what this means is that in this design, because we know that router 1 is connected on this port of the switch, we have to go on the switch and configure this port to be DHCP snooping trusted. Which what this means now is that when router 1 is going to send a DHCP server type message, like DHCP offer, the switch is going to allow it because it comes in a trusted port and send it, of course, out of the client. But when the attacker sends a DHCP server type message, a DHCP offer, because it comes in bound on an untrusted port, the switch is going to drop that packet. So once we enable this capability per VLAN, the switch intercepts all DHCP messages from untrusted ports only. And this makes sense. Again, whatever you read, it has to make sense. Because once you go on the switch and you tell the switch that a specific port is trusted, if it's trusted, then why would the switch intercept DHCP messages on that port? Because you told him it's a trusted port. So the switch trusts that port, which means all DHCP messages received on trusted ports are not inspected.